Hello, Ling 441. Today I'm going to talk about exemplar theory, or the exemplar theory of speech perception, kind of as a nice little follow-up, or what I think is a nice little follow-up to our discussion of hearing or audition and motor theory in a couple of previous lectures. But before we actually get into this, I want to make sure that you have done this experiment, which is called the continuous word recognition experiment. I'm not exactly sure how I'm going to post it. Again, I'm recording this in the summer, a few months ahead of time, but whether this is online on my website or whether you just get this through a PowerPoint that you download from the course website, please do this experiment. It's the one where you listen to a series of words and determine whether that word is new or old, whether it's been repeated before in the list. Do that because that's going to come into play as I work through this lecture, and I want you to kind of have the experience before I tell you what it all is supposed to mean. So yeah, with no further ado, let's talk about the exemplar theory of speech perception. Right, so the way I normally get into this is by having you guys do a little pop quiz in class. So I'm going to put up a series of pictures here on this first slide, and I'm going to have you tell me whether you think each thing you see is a cat or a dog. So this is a different kind of perception experiment. I guess you could say it's not really about speech, maybe a little, but either way, let's see how you do. So is this a cat or a dog? How about that? Or this? Or that? Or this? Or that? Or this? So on and so forth. What are all of these things? If you're like most of my students, you got 100%. Sometimes this guy down here in the corner throws people a little bit, but I'm pretty sure that's a dog. And now that you've scored 100% on this pop quiz, maybe you can tell me how you did it. What did you see in these photographs that told you whether each one of these things was a cat or a dog? Do all the cats have something in common that you can kind of latch on to, which make them look different from the dogs exactly? And if so, can you tell me what that is? There might be something maybe that you can look at, say, well, I don't know, the cats kind of have pointy ears, but then this dog has pointy ears too, so on and so forth. I don't know, maybe something in the eyes. There's something there, right? But when you stop and think about it, it's kind of hard to like put your finger on what exactly it is. And we know we've seen lots of dogs and cats in our lives, right? And the dogs can take all sorts of funny shapes like this, and there are probably funny shaped cats out there too. I just didn't look that hard to find them. But in spite of that, we usually know almost with 100% accuracy if something is a cat or a dog. How does this work? And I'll actually put a little caveat to this, that this is kind of a special case. You can kind of consider these natural categories because these are two different species of animal. But the world of cats and dogs has been highly, or like I guess you could say the phenotype, the way they look, the way they're shaped has been highly influenced by human beings over the many years of us living together with cats and dogs as animal companions, because we've kind of bred them to look and function in different ways, has different sorts of working dogs or toy dogs, so on and so forth. But in spite of all that sort of human influence, there's still kind of there's still natural categories, right? A dog is still a dog, so it's still within the sort of the framework of natural dog or dog variation that we're used to sort of processing, and we can still identify whether a dog is a dog or a cat is a cat. But how we do that exactly, that's not something we really have good conscious access to, I guess you could say. A little bit like the motor theory of perception, but in a different way. So what I'm trying to get into here with lots of rambling at the beginning is that we're going to think a little bit about how we categorize the world as we get into today's lecture. And a classical answer for how we categorize the world, and which is kind of the default way we tend to think about it when I sort of pose a question like, well, how do you identify whether a cat is a cat or a dog is a dog, is to say that we rely on properties of the object or the thing we're considering. So when we look at cats or dogs, we want to say, well, what is the features what are the features that cats have that dogs don't, or vice versa. And yeah, so I think the first time I put this together, the reason I glommed onto the pointy ears thing is because I didn't have this husky guy over here in the left-hand corner. So everyone's like, oh, the cats have pointy ears. But of course, dogs can have pointy ears too. That is a funny way that we have actually influenced the world of dogs, is that wolves don't have floppy ears like, say, a golden retriever would have. So that's something that through breeding or domestication, I guess you could say, dogs have developed less kind of rigid ears. Anyways, be that as it may, some dogs can still have the pointy ears. There's no one property I don't think you can pick at. Maybe on this, maybe the whiskers. This dog kind of has whiskers. That is the thing to say is, well, that's a cat or that's a dog. But in the classical world, that was exactly the way it's supposed to work. So all members of a classical category are supposed to exhibit the same properties, and no non-members of a category are supposed to exhibit all of those same properties. So there's winds up being a nice, clear dividing line between things that are members of a group and things that are not members of a group. And also, there's another kind of dividing line you can get out of this, such that there are properties which define the members of a category. But since the members of a category have more than just those definitive properties, they also have what are called incidental properties. Another kind of maybe natural category you can think about is, say, men versus women. That's kind of been a topic of some interest. Well, not just for the past few years, for a long time, but in recent years, people have kind of thought a lot about sort of like the fuzzy area between the two groups. But say I'm a man, whatever definitive properties you think might exist that define a man as a man, say having dark hair is not one of them. I have a beard, which is typically associated more with men than with women, for sure, but not all dudes have beard, right? So some of these are incidental properties according to the classical model, and others would be definitive. We don't have time to get into it with what those definitive properties might be for men and women, but you can maybe think about whether you can get some that would work, just like the difference between cats and dogs. I'll give you kind of an easier example, which is not really a natural category as we normally think about it, but is a kind of abstract mathematical category, which this analysis works better or more easily for. So in Euclidean geometry, the kind of geometry that most of us learned back in high school or whenever, you can think of a rectangle, which is defined as having these properties. So a rectangle has four sides. It's two-dimensional. That's maybe kind of implicit. So this makes it what we call a quadrilateral. But then it also has four right angles, which is kind of where the name comes from like right angle, rect meaning right. So I've got the name of the thing in the thing itself. But we can add another property to that and say that if it has four equally long sides, then it's a square. So now we have two different things which are clearly defined or differentiated by this one single property. So this works nicely in the abstract world. And I'm going to add another property to the square definition, which is not a definitive property because I'm going to make the square red. So as before I said I have dark hair. That's like an incidental property of me being a guy, or just me being who I am. It's incidental to the fact that I'm a guy. The fact that this square is red makes it incidental to the fact that it's a square. These are the things that define it as a square. This is just part of what it is, aside from that. If you go back to the history of philosophy, there is a famous philosopher named Immanuel Kant who kind of spent a lot of time trying to figure out how we sort of organize the world mentally. And part of his theory about how we categorize the world is that there are properties which are substance and accident, which for me, when I first learned about it, was just a funny way of making it a distinction to say things are substance and accident, but this is the substance of a square and this is the accident of a particular square. You can think about that as well using the terms I gave you before. These are definitive properties up here for this thing, and this is an incidental property. Before I move on from this hopefully helpful example, I will tell you that I learned something about the history of Calgary a while back, which I think is still kind of amusing. But if you remember, or if you remember, when I moved here, the tallest building in town was the Petro-Canada Tower, which is red, as you might know. And Petro-Canada was an organization which was begun as a crown corporation, so it's basically the government running the company. I think back in the early 80s, when the government was doing things which were economically disfavorable to the oil industry in Calgary. So people in Calgary got upset about that. That was also during the Cold War. And so when Petro-Canada started as basically a not free market corporation, the people in Calgary called it the area where the Petro-Canada building is downtown Red Square, because that's, I guess, how communists would run an oil company. It's not exactly that way anymore. The tower's still there. It's no longer the biggest tower in Calgary, so I guess that makes some people happy. But you still encounter older people in Calgary who are kind of upset about these things that happened 40 years ago. Anyways, so moving right along, we can think about this in linguistic terms as well. So if you go back to the sound pattern of English, incidentally also written during the Cold War, but who cares? Chomsky and Halley defined all possible speech sounds in terms of a limited number of properties known as distinctive features. And kind of this distinctive part of this is kind of what helps make them like definitional for whatever categories or natural classes they define. Natural classes being, groups of sounds that work together in phonology. So I think you're familiar with these features. Hopefully you are if you've taken phonology. They should at least look a little bit familiar from 201. So you can say like a D is a coronal sound. It's voiced. It's minus continuant, which means it's like a stop. It's minus nasal. And then, we can switch these feature values around one by one. So if we switch the nasal specification for this guy, it becomes an N. These other features remain the same, so on and so forth. That's how the distinctive feature set works for the sound pattern of English model of the phonological world. These are like classical categories because they're defined by specific properties, which are different from one group to the next. When I was in grad school, I learned that similar approaches have been applied to syntactic analysis. I didn't go much further with syntax than this, because as you know, I prefer the sound world, but in theory, you could try to make it work, right? So the features we learned about in grad school syntax were they're called N and V. What are those supposed to stand for? It's hard to tell. But like an adjective was supposed to be plus N and plus V. A noun would be plus N minus V. A verb would be plus V minus N. And then prepositions, weirdly, were like minus N minus V. So this was just kind of curiosity, like a historical curiosity when I learned about it, and I didn't think about it any further. But then I learned many years later that Betsy Ritter, our esteemed syntax professor, has done a lot of work in these sorts of features in syntax. So you can keep going with this and applying sort of this classical model to the way that language works. But language has proven to be a fertile soil for understanding how other models of categorization work. In particular, there's a different theory of how we categorize the world called the prototype theory of categorization, or you can think of it as the prototype theory. And this was first espoused or elaborated on by a psychologist named Eleanor Rosch in the 1970s. And she called into question the idea that the classical category system has any validity for the way that human beings organize the world psychologically or cognitively. And she found evidence that that's not the way, that in fact human beings will organize categories around what she called privileged category members known as prototypes, rather than defining categories by the properties of the elements in a group. There are specific privileged members of that group, which are prototypes, and then everything else is kind of defined by their similarity to those privileged members, rather than looking at specific properties that individual members of a category might have. And like I said, the evidence for this theory initially came from linguistic tasks, which is kind of cool. So I'll give you a couple of examples here. That one shouldn't have appeared right there, but we'll try it again. So I'm going to say just answer this question and let me know what you think. So this is a category member naming task. Can you name a kind of bird? Just the first one that comes to the top of your mind. What do you think? Did you say robin by any chance? Or maybe something similar to that? I don't know. Maybe you thought of a crow. You probably thought of a bird which is fairly typical in your own experience. A lot of people in North America will say a robin, unless you happen to be thinking about a different kind of bird for a different kind of reason. I don't know. In Calgary, I have encountered a lot of magpies. There were no magpies in the world where I grew up, so they're kind of distinctive for me. But I still think of robins as like a sort of default type of bird. When I was in kindergarten, my teacher told us all that when you see the 7th robin in March or April, that means that spring has arrived, and I've not forgotten that since. So this can vary a little bit from culture to culture. Like if you live in a part of the world where robins don't exist, you might name another kind of bird, but it's probably going to be a bird that you're used to seeing. We'll try another linguistic task here, if you're ready for it. So, is a robin a bird? You probably said yes. Is a penguin a bird? You would probably say yes after you think about it for a little while, right? So a robin is kind of really in the wheelhouse of what we normally think a bird is. So it's easy for us to say, yeah, that's true. When we say, is a penguin a bird? We're like, okay, sure. It doesn't fly, and it lives in Antarctica. But other than that, sure, like taxonomically, it is a bird. So, all right, it is easier to do this. You can do it more quickly when you're dealing with like a prototype bird than when you're dealing with a non-prototype bird or a bird that's sort of on the periphery of the category. So the taxonomy system in biology, as far as I understand and believe is to be the case, still operates in terms of like classical categories, because that gives you nice kind of clear dividing lines between what's a bird and what's not a bird. And I don't know exactly what the specific property set is for a bird in that categorization scheme, but it puts penguins in the bird category and it puts other things outside of it. So whatever those properties are, they're not as important to you as sort of the specific example of like a robin. That's, yeah, obviously a bird, right? So we can think about this. I've got a little graphical depiction here. Maybe it's helpful, maybe it's not. But basically we're saying that like a robin is like a prototype bird. So anything else that we encounter in the world, we will consider a bird. Doesn't have to be official, it's just the way that our minds will categorize it. Anything else that is a bird is considered a bird by our minds to the extent that it's similar to this prototype. So like a crow is pretty similar to that. I see ravens around here. They're fairly similar to, well, robins, at least in the way they're shaped. They're a little bigger, but they also look like crows, so there's similarity there. Something that's a little less similar and maybe is not as common in your experience is a hummingbird. So that's relatively close, but still not the prototype. Like a buzzard or a vulture is something that you probably haven't seen a whole lot of. Still technically a bird, but we're getting closer sort of to the periphery of the category here. We can keep moving out. Like, so we have ducks. There's red-winged blackbirds. I walk by them every night when I go for my little walks. They're kind of similar to robins, and they're a very nice Alberta bird. I see ducks on my walk too. They're different though because they spend a lot of time swimming. We don't really think of birds as swimming things, but there are obviously swimming birds, water birds. Toucans. You probably haven't seen too many toucans around Calgary outside of the zoo. I'd be really surprised if you've seen any actually. But they're birds, right? Pretty flashy. So other kind of really odd birds are like an ostrich, which doesn't really fly much at all. And again, you probably haven't seen one outside of the zoo. And if you have, you're lucky. Hopefully it wasn't chasing you. And then like a penguin is way out in its own little world, right? But this is how the category is supposed to be organized. These are all in some technical classical sense birds because they all share whatever properties they need to. But what a bird is to us is something like a robin, is what this category model is saying. We can look at a sort of third view of how to organize categories by taking the prototype idea like just one step further. So this is the exemplar model of categorization. Again, this comes from cognitive psychology as well. So this is just a few years later after the Roche proposal and her findings in the mid-70s. So these guys, Medin and Schaefer, were first published on this, and they just said, we'll take the prototype model one step further and say, just we have categories, and they're defined not by properties, not by a special, individual in the category, but just by everything that's in the category. And this is weird. It's kind of oddly anti-intellectual to say, well, there's nothing sort of you can hang your hat on with a category to say that's what defines the category, other than the stuff in it. But the point is that taking that approach, making that assumption in your model can help explain what people actually do. So whether or not it's satisfying to you as a linguist or as a thinker, it may be how the world actually works. So their idea is that categories are defined by extension. So everything in the set of the category bird is what defines the bird category. So this is just borrowing a concept of from set theory and semantics that the things in a set are its extension. Neither prototypes nor properties are necessary in this model. And then the way that you figure out if something is in that category is not by looking at, what properties does it have? You don't look at how similar it is to the prototype of your category. You just compare something which may or may not be a bird to all the birds you have in your memory. And you kind of judge similarity on a case-by-case basis with every bird in your mind. And then overall, you say, well, that's pretty similar to a bird. Sure, I'll bring it into the club. Or you say, no, that's not a bird at all. That's a dinosaur, or that's a marsupial or something. So I'm going to plop that into a different category based on how it matches up with what I've already experienced or know. But this is something which is different from sort of using definitional properties, because you don't have a clear set that you hang on to for the rest of your mental existence. Instead, generalization happens on the fly. So if you bring in a new exemplar into your category, then that category is going to shift a little bit in terms of how you understand it. And you can kind of expand it and have it move around a little bit in similarity space. So this is cool. One of the things that's cool about this is that we have to think a little bit about how this process of generalization actually works. When you look at generalization in a classical model, you just say, well, does it have those properties? Yes. Okay, it's in the category. That's how you generalize. But when you do it in the exemplar model, when you think about generalization, it's a process that happens over and over and over again. This is something that human beings are really good at doing. How does that actually work? Maybe there's a little more that goes into it than just identification of property, boom, we're done. So what you wind up having, I'm going to give you a bird category model again that's going to look a lot like what we saw for the prototype model. And again, I'm kind of spacing these out with respect to their similarity to one another. So a robin will still be more or less in the center of this category, because the robin is going to be sort of most similar to all the other exemplars in the category. And a crow is pretty similar to a robin. Moving out here, we probably have more distance between these two guys. Actually, I don't know, hummingbird probably shouldn't be over here because it's not very similar to an ostrich or what have you. But the things that are more distant are supposed to be less similar here. But on top of that, what you get are more than one token of an individual type of bird. So you can get lots of tokens of robins, which you probably have in your experience. You probably have lots of tokens of seeing mallards out in the world. So there's more than one of those. And that can wind up having an influence on how you generalize on the basis of these things. So you're comparing a new thing that you see in the world to all your tokens of bird in your mind. And if there's something that's pretty similar to a robin, you're going to sort of be more influenced to thinking, well, that's a bird, because it's so much very similar to these other things that I've called bird every single time in my life before. And you might have a few more tokens of crows in there as well. And, maybe you've seen a lot of robins or one or two hummingbirds in your life or something like that. And so you don't get that sort of added bonus benefit for these kind of odd birds, which we don't really, I don't want to call them odd. I don't want to discriminate, but we don't see them that often in Calgary, right? So you've probably only seen these in the zoo, or unless you took a fancy trip somewhere, which is nice. You maybe have seen a buzzard every once in a while driving out on the highway, but they're just not common, right? Or same thing applies to penguins. The ones that really count are the ones we've seen a lot. So they wind up defining birds for us more for that reason than sort of the particular properties they might have. Or the idea that, robins might be special in a way that crows are not, something like that. Okay, so when people used to talk about categorical perception in speech, we're going back to speech here, they meant perception of classical categories. So you can think about this. The very first categorical perception paradigm was looking at what properties kind of define different places of articulation for stops. And they were trying to figure out how transition cues feed into that. So the theory they came up with is that in categorical perception, you hear something and you apply a label to it, and then you just wind up working with that label when you do a discrimination task afterwards. So a stop winds up being either a B or a G, and there may be a little bit of leeway in how often you sort of label a particular stop as one or the other. But once you get there, then that's what you use. Your mind just kind of abstracts it into that category, and that's what you use for interpreting the rest of the world whenever you hear that same sound. The important point is that in your mind, there's not supposed to be any in between between a buh or a guh or a ah, da, that sort of thing, right? So in classical categories, as I mentioned before, there are definitive properties and there are incidental properties. And if this model is supposed to work for natural speech stimuli, then we should be able to figure out at some point what these definitive properties are for these speech categories as opposed to their incidental properties. What are those properties that define a stop category? So we looked at this, and acoustically, it's a little tricky. There seems to be some fuzzy boundaries, right, in between the different categories. So you might rather think about this in articulatory terms. It's kind of easier to say, well, a ba, you're bringing your two lips together to make a stop, and the flow of air is stopping in your mouth. And maybe that works better for ba than it does for most other types of categories of sound, or at least consonantal sounds. But kind of the thrust of the matter is that you're making this sort of intellectual assumption that the definitive properties that you're looking for have to be invariant. They have to be shared by all category members. So even if you can't find something that's consistent every single time over and over again for a b, acoustically, if it's easier to find articulatorily, then it's just better to define the category in articulatory terms, right? Because you want something that is consistent and common and shared by all category members. You use those properties to sort of do the generalization work for you. So what are the invariant properties of stop categories? I've got a little diagram here, which I like to use to show you that it's very difficult to get this to work at the acoustic level. So people have looked long and hard for invariant acoustic properties of stops, and they haven't sort of really found the definitive thing yet, but some people are still looking, which is kind of fun, because, never give in, never surrender. Here's some evidence that is kind of relevant for this that was published back in 1952 by some of the first guys from Haskins Labs who first came up with the theory of categorical perception in the first place. So they had done this study, again, with the synthetic speech produced by the pattern playback speech synthesizer, where they were looking at sort of bursts, release bursts that were synthetically produced that had different frequencies, and then they were played in different vowel contexts. And they just asked listeners, like, well, what do you hear when I play this burst for you? And again, this is odd because it's a synthetic speech and it's not great synthetic speech to begin with. So it's a far cry from what we're used to doing naturally as speech perceivers. But they still got this data, which is kind of fun to look at, I think, because they got this pattern here in the middle that looks like a shark about to eat a pea here. But the way you interpret this is, well, in the context of the vowel E, these release bursts they sound like P's up until about 3,000 hertz or so, and then above that they sound like T's. And in the middle, when you start playing them next to other vowels, we get this complex pattern where next to A's they sound like P's sort of at this frequency, P's at this frequency range, T's at the high frequency range again. And then in the middle they wind up doing like a split. So they wind up sounding like Ks at this lower frequency and Ks at this higher frequency, but not consistently all the way through. So you can keep going and walking through the different vowels to get the different patterns here. And it's for the back vowels, you get better K responses for lower frequencies because that's where we'd expect Ks to be, backer anyways, rather than front vowels like up here. But it's hard to kind of pick out one thing here that shows you the dividing line between P's and K's. The P's are kind of split up into 3 different sets anyways. So the classical model for this is a little bit strained. You have to take vowel context into account and then do a few other mental gymnastics to get it to work. So since variant and acoustic properties couldn't be found, especially for velars, which are kind of not really invariant at the articulatory level anyways, then it was assumed that listeners perceived gestures, not sounds. This is one of the sources of the motor theory of perception. I'm not discounting motor theory completely because there's something there about how people actually are sensitive to gestures when they actually do perceive speech live. But actually spelling out what they're responding to or what they're picking up can be tricky because then you also have to say, well, what are the invariant articulatory properties that define stop categories? And this is tricky as well for velars too because velars can move back and forth in different vowel contexts. So there's sort of not one thing there that makes it make sense. The motor theory itself talks about speech being a code rather than a cipher. So like in a cipher, you take an alphabet and you say, well, A equals 1, B equals 2, C equals 3, so on and so forth. And you can just kind of make a clear translation between the two. But in a code, the idea is that it's more complicated than that. You can't just do a one-to-one correspondence between what you get on the acoustic surface and what's underlying articulatorily for that particular sound. And it's a mess. Actually, they kind of use the metaphor and I don't know if I should really be telling you this metaphor, but it's famous in the world of speech perception literature that you take a series of eggs that are dyed in different colors and you roll them all through a ringer, and they're not boiled, they're just raw eggs, but you paint them different colors and you roll the whole thing through a ringer, and then on the other end comes this gooey mess where all the colors are kind of mixed up with one another. But you can kind of get a sense of how they go in order. And so your mind is supposed to be this magical special thing which can say, oh, I can figure out what the original order was. Okay, maybe that works, maybe that doesn't. That's more what's going on rather than just a one-to-one correspondence between the two. And either way, it's tricky to figure out what is invariant in that. Maybe our minds need something invariant, maybe they don't. So the sort of second revision of motor theory as it kept going through intellectual history is that rather than perceiving specific places of articulation in a stop, listeners perceive what's intended. They perceive what the eggs look like before they went through the ringer. So the problem with this, it gets a little bit awkward because intentions are kind of impossible to observe, right? We can see actions that human beings perform or that, animals do or what have you, where they sort of stop when they reach a goal. And then at that point, you can kind of infer, well, maybe they had the intention in mind that they were getting to that goal. But you can't really see the intention before that happens. And then you just kind of work backwards from that, right? So the idea is that those intentions are in their mind. They're trying to complete some action. As observers, though, saying that we perceive those through motor theory or whatever sounds nice, but it makes it kind of impractical because those intentions are impossible to observe directly. Not that they aren't important. The main goal, though, is to at least get to a point there where the intentions might be invariant. But maybe what we don't need to do here is to assume this sort of invariance. So everywhere we look in speech, we find lots and lots of variation. So if you look at, say, the acoustic properties for vowels, not just thinking about stops anymore, but this is data from a classic study back in the 50s as well, from a couple of guys named Peterson and Barney who are working in Michigan. And they just brought in a whole whack of people, men, women, and children, and said, produce these vowels for us, and we're going to measure your formant frequencies. And what they did is they plotted all the formant frequencies in this graph, It's a little bit different from the way we're used to looking at formant frequencies because it's plotted in a normal mathematical way with the origin of the graph down here, and then F1 increases here and F2 increases here. So it looks funny, but also part of it is you can see, well, oh, here are male formant frequencies, they're lower. Here are the female formant frequencies, and here are the kid formant frequencies. And you get lots of, and they tried to draw circles over the sets of common vowels as they were produced by these speakers, but they, even though it looks nice at a higher level, it gets pretty messy as you look closer and closer at the details. So like here's the set or category, if you want to call it that. There's a lot of as here. There's some is in here as well. Here's the category here in the middle, which kind of overlaps with a number of things. Here's where and all come together. Here's and oo and all kind of glomming onto the same space. So there's lots of overlap. It's hard to kind of get the clear invariant dividing lines between these various categories. And of course, there's this point as well that I mentioned, that you get clear, consistent differences between men and women, and also between children as well. So there's variation in tokens. There's variation between speakers. One speaker to the next might produce these vowels in a different way. There's differences between genders. There's differences between dialects. This was done in Michigan, and you'd probably get different results if you did it in California or New York, or for that matter, Australia or Britain or India or wherever, right? There's differences between age groups too. There's variation everywhere we look in speech. It never goes away. It's a lot easier to find the variation than it is to find the invariance. So variability, if you're thinking that you're trying to pin down something invariant when you're categorizing the world, variability becomes a huge problem. But an alternative is to say it's not a problem. It's not a crisis. It's an opportunity. Instead of sort of trying to get rid of all this variance to get at the invariant core, you can say, well, why don't we just use it? Because it's always there. We can it's super dependable. We can rely on it. So I'll give you one example of sort of how thinking has changed or developed on this line of research. So this is looking at sort of the prototype model of how to categorize speech. And this is research that came out of the early 90s. So this is a sort of simplified model that's saying that you're defining categories by individual prototypes. And this is using those prototypes to identify vowels in speech. And it's kind of easy to think of how that works because we normally have a sense of where the vowels line up in formant space, right? So we can kind of pick out little sort of, capitals of each domain of vowel in that space and say, well, that's where the prototype is. This finding is known as the perceptual magnet effect, and they did it in a slightly more sophisticated manner than just saying, oh, here's the capital of E versus the capital of Oo town or whatever. Anyways, so what they did is to try to pin down where those sweet spots of each vowel are. They played listeners a continuum of synthetically produced vowels in the neighborhood of the vowel E. And then for each one, listeners had to give sort of a gradient measure of how much each one sounded like E until they got into sort of like the neighboring categories like A or I or something like that. So they found that some vowels get better ratings than others. Some synthetic vowels get better ratings than others. And again, they're only varying by their specific formant frequency in the center of the vowel. So some were judged to be prototypical. Others were judged to be non-prototypical or more peripheral in the category. So then they had part 2 of this study, and this is also plotted out in a mathematically normal way with the origin of the formant graph here rather than up here in the upper right. So then they said, okay, listeners, we're going to give you a specific vowel token, and that's going to be your vowel category center. So we're going to play you that vowel center vowel and then another vowel, and you have to judge whether the sort of questionable second value here is more aligned with this category center or more aligned with this category center. So they were plotting or playing vowels along synthetically produced continua again. So this, say, is supposed to be the prototypical center for E. It's the one that was judged as like a good example of E in the first part. This is a center of a second category, which in the first part was not judged as highly as a good example of E. And so then they're playing these other vowels along these spokes of these, I don't know what you want to call them, vowel sets. And kind of the crucial one is to say, well, if I play you this one in the middle, that's like halfway between this non-prototypical category center and this prototypical category center, which way do you go with that? Do you think it's more like this one, or do you think it's more like this one? And they found that people judge it to be the same as this prototype vowel more often than they judge it to be the same as this non-prototype vowel. So there's kind of a shift in perception where you think that things kind of in the middle here are more like a prototype rather than a non-prototype. So there is something in this model which seems to be special about the sort of prototypical vowels that we're used to hearing, or that we perceive as sort of the best exemplars of a category. And their theory was that you kind of define an entire category based on these centers. So whatever sort of new token you hear, you kind of glom it on to the category that it's most similar to, defined by that prototype. Whichever prototype in the vowel space, the sort of new token you're hearing, whichever one it's closest to is the one that you perceive it as, rather than perceiving it as some just random other spot in the perceptual space. They called this the perceptual magnet effect because the prototype kind of drags the unknown token closer to it to belong to its category rather than the non-prototype. I think about this as well. Say if you, because I like to read about astronomy and physics in my spare time, if you can believe it, but this is sort of like a massive body in space, which will warp space around it because it's so massive, it has a huge amount of gravity, and everything just kind of gets sucked into it. Like, the sun is a magnet in some sense just because it's a massive body, so anything kind of closer to the sun will get sucked towards the sun rather than the Earth, which is like a much smaller body in space. So if that helps you to think about it that way, go ahead and do so. Yeah, so the perceptual magnet prototypes with in that previous study, which was done by Pat Kuhl in the early 90s, they are usually located at a listener's average F1 and F2 values for E, which is kind of neat. And they also found, they looked at whether babies do this, and they found that they do. Pat Kuhl has done a lot of research over the years with infant speech perception. I can't remember the exact details of how she showed this, but it's pretty neat the way they get it to work. They tried the same thing with monkeys, but the monkeys didn't do it. So again, this is kind of looking at maybe like there's some specialization. I don't know if you want to call it a module or not, but human beings seem to be specialized from this from birth practically in a way that other animals in the primate world are not. So in this model, the prototype is the only thing that has to be invariant about the category, and the particular properties aren't as important, but you're kind of still using properties like formant values to judge similarity to the prototype. But the prototype is what defines the category and not some specific dividing line in the vowel formant space. Going back to that Peterson and Barney data I showed you before with all the variation in it, if you apply this sort of prototype model where you define each vowel by sort of the center or the average values of the vowels that were produced by the speakers in that study, and then you try to classify all the tokens on the basis of those category centers, then you find that this prototype model would be at about 50% correct. The human listeners, and people have done this in subsequent studies from Peterson and Barney, but human listeners, if they're identifying English vowels when all the vowels are thrown into the mix, they will identify those vowels correctly 94% of the time. So human beings still aren't perfect, which is kind of another reason to believe that maybe there's nothing invariant there, because people are still making mistakes with them, even though they're expert listeners by the time they become adults, right? So the prototype model does okay. It's doing better than chance for sure, but there's a lot of room for improvement here. So variability is still kind of hard to deal with, even in the prototype approach. And I am going to pause here and pick up with the exemplar approach in the next half of this lecture, but I just kind of don't want to overwhelm you with too many anecdotes and too long of a lecture and any one video anymore. So I'm going to pause and pick it up again after the break.